My name is Jorge Vega. I'm a power electronics engineer working for Northrop Grumman. I specialize in design of resonant converters. I'm also a PELS member. Today, I'll be walking you through a issue that I had in the lab concerning measuring frequency response. And the solution was quite revealing. I hope that you enjoy my video, and if you have any questions, please reach out to me. Thank you. I'm going to walk you through a problem that I had recently while measuring frequency response on my buck converter. The problem was very unique because it dealt with duty cycle. Let me draw the circuit for you, and I can walk you through the setup, and I can walk you through how I solved the problem, and hopefully the problem that I had can benefit you as you debug frequency response issues that you may have while making your measurements. So the circuit that I had was a buck converter, kind of looked like this. Okay, so load. This is the in. This is the controller. This is the output of the controller, and it controls a gate driver. Okay. This is the feedback pin, and this goes into an amplifier. It looks like this. And then this is the comp pin. Okay. And in between the comp and the feedback, we usually put our feedback elements. And for example, in a type 2 compensation circuit, we could have something that looked like this, right? Anyhow, this here is what I like to call the R injection. This is our top of the feedback. This is our bottom of the feedback. Okay, and your network analyzer, it could be a 4100, for example, or any other network analyzer for that purpose. There's usually three ports to that. One is the injection port, another one is the reference port, and another one is the T port. So the injection port usually comes to an injection transformer. And the reason we need an injection transformer is because we are injecting a disturbance here in the loop, and the way that we do that is by um, using an injection transformer. We apply a sine wave here, but we need that sine wave, comes like this. We need that sine wave reference to this point. Okay, so it would look like that, right? This sine wave is reference coming out of the instrument. The sine wave is reference to the internal reference of the instrument, the same as the T port and the R port. We don't want that. We want the sine wave to be referenced to this point in our particular case. The reference was connected like this. Okay, it would come there, and then the ground of that would come here, and then the T is connected to the output, right here, and then the reference comes here. So this is essentially my circuit, and what I like to highlight is the comp pin and the feedback pin. Okay, I want to make sure that that is clear here in the drawing. The way that we usually test this is we test 5 corners. I like to draw a square to show that. This here is low line minimum load. So this is low line, and then this is minimum load. Okay. This one here is low line max load. This here is low line, I'm sorry, high line, minimum load. And then this one is high line, maximum load. And then the fifth corner is this one here in the center. And that one is typical. It's right there. The issue that I was having was that I was successfully getting, I'm going to draw it right here. You know, I was successfully getting a Bode plot for these corners of my test matrix, but I was not getting a Bode plot here. And the low line maximum load corner is the one that is the most stringent. So essentially, for this corner, essentially for the rest of the corners, I was getting a Bode plot that looked like this, textbook Bode plot, kind of look like this. So this is phase, this is dB. This is the crossing, right? This is 0 dB, and this is 0 degrees. Okay. When I make this measurement, I typically I am also using a scope, and I'm using it to get the switching node. So this typically goes to channel 1, this goes to channel 2 of the scope. So it kind of looks like this. So I'm monitoring the switching node, making sure that it looks healthy. That's what I've drawn here. And I'm also monitoring the output voltage. It looks like that. So I was getting, so this is the output. Okay, and then this is of course the switch node. I was getting this for these 5 corners. But for this fifth corner, which is low line maximum load, I was getting something that looked like this. Essentially noise. However, the scope showed a clean switching node. Oh, a clean switching node, like that. And the output voltage, well, because it's loaded to maximum, um, there was a droop to it, okay, but it was still within the window of regulation, and that's important because from a requirements point of view, I still meet requirements. Means that the power supply is still working the way that it's expected to work. So typically I use plus minus 5%, at least for this particular application, right? This variation here was plus minus 5%. And for low line maximum load, the output was still within the regulation limit. So that didn't pose a problem. So this here was source of concern. Why was I getting this? And this is what I was trying to debug. So there are several reasons why you could get this. And that's what I would like to walk you through. One of the reasons, is that it could be a test issue. Okay. Being a test issue, it could be maybe that your oscillator is too small. Okay. And when I say oscillator, I mean the injection port of the network analyzer. So the injection port is this port is outputting a sine wave, and you can change the magnitude you can change the amplitude size to that sine wave. And what it does is that the network analyzer, it's sweeping it across frequency, right? But you have a knob in there or a setting where you can change that amplitude. So if it's too small, and I'm going to draw it right here, if that is too small, you're going to have uh, something that looks like this. You're going to have a lot of noise. Then it's going to go like this. Okay. All right. So this is the signature of an oscillator that is too small. And if it's too small, then you're gonna have noise throughout. The other thing that could happen is that the oscillator is too large. And if it's too large, then you might have something that looks like this. So this is dB, this is phase, this is dB, this is phase. You might have something that looks like this. It, it you you might have a frequency response plot that begins okay, but then it devolves into noise. So in my case, I was getting noise which was indicative of something of this nature. Another reason that you might be getting this type of behavior, well, is that maybe your power supply is unstable. And if it's unstable, then you're not only going to be getting noise, but your switching node may be jittery. In other words, you may have, I'm going to draw it here. You may have something that looks like this. You know, just different 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 pulse widths. And the reason for that is that uh, well, the power supply is not stable. You're going through different. The power supply is trying to react to different duty cycles. Okay. A third reason is duty cycle, and that is that you have run out of duty cycle. And the way to tell if you've run out of duty cycle is by probing the COM pin. Oh, the COM pin has a um, minimum and a maximum, and you can look at that. You can find those numbers in the data sheet. So in my case, I was working with an ISL 78841, which is a very simple controller. And the reason I was using that is because the applications that I work with are space applications, and I needed a radiation hardened device. And this is typically the go-to device that I work with. In my case, in this case, the duty cycle is limited to 50%, and the comp pin can go has a limit of 5 volts. Can go from between 0 and 5 volts. As I debugged my circuit, I probed the comp pin, and what I discovered, I'm going to plot it right here, was that it was pegged at 5 volts. So this is the comp. So this was at 5 volts. What did that tell me? That told me that I had barely run out of duty cycle. So as I swept V in, uh, from minimum, from typical to max, and as I swept the load from uh, minimum, typical, and maximum, the corner test for minimum input voltage and maximum load is the one that requires the most duty cycle. So in this case, I had just exceeded that. And because of that, because of that, I'm not able to get a frequency response plot anymore. Why am I not able to get one? Well, because my power supply is now running open loop. And the implication of that is that I am not benefiting from negative feedback. So uh, if if the input voltage to my converter has wiggles in it or noise, that noise, the negative feedback in the power supply attenuates that noise. So that now is going to become so many dBs less at the output, right? Uh, If I'm running open loop, I don't have negative feedback to be able to do that. And then if the load becomes a step all of a sudden, the the power supply will not be able to react uh, in a timely manner to address that step. So those are some of the implications of running open loop. Even though Even though the power supply looks like it's behaving well, you're gonna be having those type of issues. So this is the presentation. What I walked you through was some of the issues that you may encounter if you're making a frequency response measurement and how you debug it. What I recommend that you do is that as you take your frequency response plot, you have a scope right next to it that shows you the switch node, the output voltage, and the comp pin. So this is the big takeaway from this video. As you get your frequency response, plot the switching node um, along with the comp, know what the limits the comp pins are, and that'll tell you if you're running out of duty cycle. Thank you very much.